Okay, let's get started recording. Geologic processes on Earth. Outline, 3 main points. First, introducing geology. Then some processes on Earth, actually inside Earth, like tectonic plates, important concept, continental drift and so on, volcanoes and earthquakes, and then the rock cycle, the various types of rocks, weathering and erosion, and so on. So, first point, geologic processes. Earth is some 4.6 billion years old. It's the only known habitable planet so far. Has the right temperature, atmosphere, and gases for life, and has a magnetic field that shields it against solar wind. The inside is really hot. The core is made out of iron mostly, while the mantle is made out of rocks mostly. There's a thin outer layer, silicates or rocks, as the crust. Right. These are continental and oceanic crusts. So this is it. The radius is 6,371 kilometers. The crust is really thin, and so on. So we said that early Earth was full of toxic gases, like volcanoes released sulfur. It was really nasty. Water vapor trapped in magma got released to form oceans through volcanoes. The original atmosphere was saturated with carbon dioxide. Primitive algae absorbed carbon dioxide and water and produced oxygen and carbohydrate. These are favorable for basic life that started 2 to 3 billion years ago. Started in the ocean. Earth hosted animal life for some 600 million years, the last 600 million years. Complex life. Humans have been around for about 1 million or so years. Earth's heat engine, it's internal to Earth. It drives magma, drives tectonic plates and so on. Planets like Mars, Mercury, and Venus do not have such a heat engine. Heat convection inside Earth drives volcanoes, earthquakes, and plate tectonics. Actually, plate tectonics and volcanoes for mountains. We will see. We said that igneous rocks formed when lava cools down. Weathering and erosion grinds mountains down and transports sediment to the ocean. So we said that volcanoes form mountains, weathering and erosion grind them down. We said that tectonic plates move, they spread apart, they collide, and they subduct one under the other. The continental crust is formed of granitic rocks, while the oceanic crust is composed of basaltic rocks. Okay, so we said, talking about plate tectonics explains a lot of things. So if you look at the west coast of Africa, the east coast of South America, they kind of look the same. Why? Because they were together a long time ago. And then continents started drifting over time. The huge continent before 150 million years ago is called Pangaea. Okay, supercontinent. Okay, all right. Right here. So this is a map 100 million years ago showing the continents. They were very, very different. There was a sea where some of the western states are right now. Look at South America. There's a big opening between the Pacific and the Atlantic. Look at North Africa, was underwater. Look at India, used to be close to Australia. And Asia, lots of oceans and seas and so on. Things changed a lot. How do we know these things? Sonar technology was developed in World War II. So in 1950s, ocean floors got mapped out. They found a mid-ocean ridge. Oceans have mid-ocean ridges. So that's where seafloor spreading starts. It's just like a conveyor belt where magma is spewing out to the right and to the left and at the mid-ocean ridge. So the oceanic crust is less than 200 million years old, while the continental crust can be older than 700 million years. So it starts out mid-ocean ridge, forms the oceanic crust, and then the oceanic crust pushes to form the continental crust and to push it higher for mountains and so on. Eras in geologic history. This is geologic time scale, 4.6 billion years ago and now. So these are eras. We said that basic life started some 500 million years ago. That's the first era of the vertebrates. Before that, there were no bones and no hard shells. So we don't have fossils. Then 500 million years ago to 250 million years ago is called the era of the vertebrates. First era. The second era, from 250 million years ago to 65 million years ago. Era of the reptiles and birds, including the dinosaurs. Actually, the dinosaurs got extinct 65 million years ago, following collision of Earth with a huge meteorite in the Yucatan Peninsula. Anyway, died out. Then the last era of the mammals, that's 65 million years ago to now. Okay? Paleozoic, Mesozoic, Cenozoic. Very good, very good, very good. Yeah, early Earth history. Radio dating allows us to find out timescales over geologic time. Like some of these isotopes can give us radio dating over long periods, like rhenium-235 or just carbon-14. It took 700 million years for heavy bombardment to stop and for Earth to cool down enough. It took 375 million years for liquid water to form oceans. And during the first eons, where there was no bones or hard shells, the atmosphere was rich in carbon dioxide. So early form of life called cyanobacteria absorbed carbon dioxide and produced oxygen. Photosynthesis started some 3.5 billion years ago. Basic life started in the ocean. Then multicellular complex organisms appeared some 500 million years ago, then plants and animals. So let's skip this one here. All right. Then processes on Earth. We said there are many glaciation periods, 5. 700 million years ago, big glaciation, what's called snowball Earth. Glaciations are caused by geologic activity. In other words, release of carbon dioxide by volcanoes. Carbon dioxide is sequestrated for millions of years deep in the magma, then gets released. That's global warming. When CO2 is released, global warming. And as we will see, weathering absorbs carbon dioxide. So when carbon dioxide goes down, it's a glaciation period. The last ice age ended some 10,000 years ago. Okay, let's talk some more about the heat engine. We said that the continental crust is 10 to 70 kilometers thick. It's granitic of origin. The oceanic crust is 2 to 10 kilometers thick and basaltic in origin. Both granite and basalt are from magma when it cools down. If it ends up in the ocean, it's called basalt. If it ends up in the continent, it's called granite. Temperatures here are very high. So let's say one or two things about this. Skip most of it. What I want to say is we see some plates, tectonic plates, and we see one plate subducting, it's ocean plate, subducting underneath another plate, and this is a continental plate. Okay? So Earth's heat engine some more. We said that the metal is very hot. It's from the silicate rocks, which are melted. Rocks melt into lava. So when you have the subduction, rocks melt, forms magma, so the magma chamber, and then spews out from volcanoes. Okay. There you go. Geothermal convection drives tectonic plate process. All right. So we said that mid-ocean ridge, right here, I think in one or two slides it will become clear. Mid-ocean ridge spreads apart, ocean crust, continental crust, and so on. Okay, some of the plates are shown here. I want to emphasize the Pacific plate and the North American plate. You see the west coast of the United States. So plates pushing into each other form mountains. This is the Rocky Mountains. Uplift. Plate collision zone is prone to earthquakes. San Andreas Fault, a lot of earthquakes, and there are volcanoes in the state of Washington and so on. This is it. Okay, so here again, mid-ocean ridge on the Atlantic, spreading of plates, then magma spewing out, and so on. Anyway, everywhere plates come together. Plate boundaries are in oceans, except in Iceland, where they meet on the continent. This is why there's a lot of geothermal energy, geysers, and so on. Let's say here we're showing the oceanic plate, oceanic crust, and continental crust. And we're showing the water level here, ocean level, sea level. So right now we see that lots of the continental crust is under sea water. But during glaciation periods, the level goes down and it's different. Well, we said that continental crust is 4 kilometers high. We said mountains are higher. Like Mount Everest, highest mountain on Earth, 8.8 kilometers. Part of the continental crust is under sea level. We said that the continents and oceanic crusts, there it is, mid-ocean ridge, seafloor spreading. This is a trench, very deep. These are called the abyssal plains. They're pretty flat. It's about 5 kilometer depth. The deepest trench is Mariana Trench, is 10 kilometer depth. And then oceanic plates push on continental plates, and their subduction and so on forms mountains and so on. Here we're showing magnetic field, West Coast United States. You see the Pacific plate and North American plate. You really see the boundary between the two. You see the magnetic field changing from one plate to the other. The conveyor belt here. We said the continental crust is much older than the oceanic crust. Oceanic crust is constantly forming. Continental crust, older. Could be older than 700 million years. While this one is less than 10 or 20 million years. Okay, let's skip this one. Skip this one, skip this one. Skip this one, this one. Okay. There were a lot of earthquakes that devastated many regions of the world. During the earthquake, there's what I call primary waves. They're longitudinal. And secondary wave, they're transverse. Okay? So primary waves arrive first and then secondary waves. Okay. Now let's talk about rocks. We said that igneous rocks come from when lava cools down. We said there are three types of rocks: igneous, sedimentary, metamorphic. Igneous is from lava. And here we're showing basalt. That's igneous in the oceanic crust, and granite, igneous in the continental crust. Okay? We said that sedimentary from sedimentation, we will see next slide, and then metamorphic is due to high pressure and high temperatures deep inside. So sedimentary, we're showing here sandstone, limestone, and shale. These two are porous, and this one is non-porous. Limestone releases carbon dioxide when it's exposed to water. Actually, rain absorbs carbon dioxide, becomes slightly acidic. When it falls on limestone, it dissolves limestone, so it gives caves, produces caves, and so on. All shale contains kerogen, oil, petroleum. Metamorphic rocks, that's if you take an igneous or sedimentary rock, it gets abducted deep down into earth, forms metamorphic rock, high pressure, high temperature. This is slate, and this is marble. Okay, let's skip this one. So there you go. Tectonic plates create mountains. Erosion and weathering grounds them down. So the rock material starts at the mid-ocean ridge, forms first the oceanic crust, then the continental crust, is uplifted to form mountains, then eroded back down to the ocean. A cycle takes hundreds of millions of years. Everything, if you go far enough, everything used to be at the bottom of the ocean, like Mount Everest. They found some limestone sedimentation, which used to be at the bottom of the ocean. So here we're showing rocks, buildup of rock layers over tens of millions of years. So you see, for example, that there was a layer here, and then there was magma. There's another layer, and then there was magma. So you can tell that this is the youngest, then this one, this one, this is the oldest. Okay, so let's show the Grand Canyon. It's about a mile deep. It took like 5 million years to form. Radio dating gives us a pretty good idea of the type of rocks and so on. Rock history over billions of years. There it is. So this is 2.5 billion years old at the bottom of Grand Canyon. And this is right now. So you see limestone, sandstone, and shale. These are sedimentary rocks. It used to be at the bottom of the ocean. The very beginning, there's granite. It's igneous. Okay? So coming from lava. It's 2.5 billion years ago. All right. We said that water streams carry rubble downstream. We said that dissolved salts are carried to the sea, making it salty, and then forming sedimentary rocks in the ocean and on the bottom of lakes. We said this is Luray caverns. When limestone dissolves, forms caverns, acidic water. Okay. Geology of fossil fuels comes from buried organic matter that formed petroleum. Slow chemical reactions over hundreds of millions of years. All shale rocks are buried 2 to 4 kilometer depth. Over the past 10-15 years, oil, shale, petroleum and natural gas helped reduce the price of gasoline at the pump. Okay, so fossil fuels migrate from non-porous rocks like shale, mudstone, to porous rocks like sandstone and so on. And this is porous, this is non-porous. So it ends up in the porous one, inside the pores. Okay, oil and gas. Okay, let's skip this one. And a summary. We said geology at work. Earth's internal heat engine drives geology. Lava at mid-ocean ridges leads to mid-ocean floor spreading. We said that the oceanic crust is constantly forming and is younger, like less than 200 million years, while the continental crust can be older than 700 million years. We said that earthquakes occur at plate boundaries. Geology builds up mountains from crust that starts in the ocean. Weathering and erosion grinds mountains down. A lot of natural disasters like earthquake, volcanoes, plate boundaries, tsunamis, in the ocean, flooding of landslides and so on. Okay, thank you very much.